So today we're going to talk about the mean value theorem for derivatives specifically. You can abbreviate this as MVTD. So since this is a theorem that has a name, the way that you'll be using it will sometimes be to justify something. And if you need to call it up to justify something, you can. It is acceptable both to me and the College Board if you justify it by writing MVTD. And it is important that you include the d because there is also going to be one for integrals, which is what we're going to do after this section. So this is specifically the mean value theorem for derivatives. Before we can get there, we have to start with one called Rolle's theorem. And so this is going to be kind of our bridge to the mean value theorem for derivatives. And here's the way that Rolle's theorem works. So let f be a function that satisfies the three following hypotheses. Number one, it's continuous on a closed interval from a to b. Number two, it's differentiable on the open interval from a to b. And number three, f of a equals f of b. And so I can kind of sketch out what they're talking about. It's maybe easier to visualize. So if I have an interval between a and b, I need my function to be continuous on the closed interval and also differentiable on the open interval. And so really practically what that means, I can't have any breaks in it. I can't, for it to be differentiable, remember, I can't have a sharp corner or a cusp. So it just has to be some kind of a smooth curve on that interval. And then also the last one is that f of a has to equal f of b, meaning the y values at the endpoints are the same. Okay, so I'll put them there, and then I need it to just be any smooth curve connecting those 2 points. All right, so I've satisfied the three hypotheses. The conclusion then says that there is a number c on the interval between a and b such that f prime of c equals 0. So there has to be at least one. There could be more than one, but there's at least one. And you can see that that's true. C would be like right about here, so that f prime of c equals 0. And that just means the derivative is horizontal at some point on the interval. Again, the conclusion says that that has to happen at least once. It could happen more than once. And in fact, in mine, you can see there's going to be probably a couple places where I have a horizontal tangent with a slope of 0. But Rolle's theorem says it will happen at least one time. All right, appreciate it. So here's a couple of different graphs that all satisfy the first three. Oh, I apologize. These are just examples of graphs that satisfy those first three hypotheses and then how the conclusion would play out. So B, C, and D are pretty obvious. A is the context where it's just a horizontal line, so every point in between A and B is another value of C where you would have a horizontal tangent, right? All right, so I'll do a quick proof of Rolle's theorem. Don't feel like you have to write this down, you don't, but just because this is a calculus class and we should be rigorous about anything we're going to use, let's go ahead and prove it. So let's look at case 1, and we'll say that's the case where our function is constant. Well, the derivative of a constant is 0. So C can be any number on the interval from A to B. Right? We saw that in the graph. If you have a constant is already just a horizontal line, so the derivative is 0 everywhere, so C is any value on that interval. All right, case 2. All right, so case 2 will look at if your function is larger than its endpoint for some x in AB, right? So that all that means is that at some point, so here's A, here's f of A. We already know that f of A and f of B have to be equal to each other. So what I'm saying is that at some point, my function goes above those endpoints. And I'm still assuming that it satisfies the first two hypotheses, which are it has to be continuous and it has to be differentiable. So no gaps and no sharp corners. So then I can say by the extreme value theorem, which we learned about unit before last, there exists a point on AB that must be a local max let's call that point, C. Since f is differentiable, the derivative at that point C has to be 0. And this is by a theorem that we also went over in the unit before last. It was called Fermat's theorem, which said if you have a local max or a local min of a differentiable function, then its derivative is 0. All right. And then the final case would be case 3. And that would just be sort of the opposite, right? Where f of x is less than f of a for some x on the interval a to b. And the proof is going to be the exact same as the proof for case 2, except instead of a local max, the extreme value theorem will say that there must be a local min. But everything else is the exact same, so there must be a local min, and at that, since it's a differentiable function, at that minimum, the derivative must be 0 by Fermat's theorem. All right. So again, it's not important to me that you can recreate this proof at all. I just think it's important that we go through the proof. Now that we can use Fermat's theorem, Rolle's theorem, which is how we're going to prove the main theorem we need to go over today, called the mean value theorem. All right. So here's an example of how we can use Rolle's theorem. And this is also a good example because the only time you guys have really been exposed to like proof in theory mathematics, which is considered real mathematics, is probably geometry. You did some proofs, but this is sort of going to be maybe your first introduction to a proof by kind of contradiction. All right, and the key to that is that we want to prove that this equation has exactly one real root. And so to prove that, the first thing we're going to do is show that there exists at least one real root, okay? So the way I'm going to do that, I'm going to name my function, let f of x equal x cubed plus x minus 1. And I'll say since f is polynomial, it is differentiable and therefore continuous. All right. And then I'll show that it has at least one real root by using the intermediate value theorem. So I'll remind you of what that looks like. So the way I want to use intermediate value theorem, I want to find an input that'll give me a negative output, and then an input that'll give me a positive output. And then since I know the function's continuous, it must have crossed the x-axis between those two values. And so just based off this minus 1 being the only constant, I know that f of 0 is negative 1, which is less than 0. And I can see that if I plug in 1, f of 1 would be 1 plus 1 minus 1, which is 1, greater than 0. So by the intermediate value theorem, there exists a root between 0 and 1. So just to visualize what I just did, we said, okay, I know that f of 0 is negative 1. I know that f of 1 is positive 1. I know that the function is continuous. Therefore, between 0 and 1, it had to have crossed the x-axis somewhere. There's at least one root. Now, it could have crossed multiple times. Who knows? It could have gone like this. But I know that there's at least one. So now I've proven that there's at least one. I want to show that there's exactly one. And here's where my proof by contradiction is going to come in. What I'm going to do is, let's assume there's more than one. And then we'll show that that's not possible. So if we've just proven there's at least one, and then we prove that it's not possible that there's more than one, the only option left over is that there's exactly one. So I'll say, assume there exists a second root and we'll call it C2. Actually, sorry. let me take that a step back. Let's go ahead and assume there exist two roots, A and B. So what that means is then f of A equals 0, and so does f of B. That's the definition of a root, right? It's where the output is equal to 0. Well, we already stated that this function is continuous and differentiable. And now the third hypothesis of Rolle's theorem is satisfied there. F of A equals f of B. So I can say, and by Rolle's theorem, the conclusion says there must exist a C on the interval between A and B such that f prime of C has to equal 0. That's just the conclusion of Rolle's theorem, right? So if there are two roots, there must be a value C in between such that the derivative is 0. But if we take the derivative of our function, we get 3x squared plus 1. Which, if you try to set equal to 0 and solve, does not give you back any real values, right? So if I set 3x squared plus 1 equal to 0, I get 3x squared equals negative 1. X squared is negative 1/3. And then when I take the square root, I get back imaginary values. So there are no real solutions to that equation. So what I can say is that f prime of x equals 3x squared plus 1 is greater than 0 for all values of x. All right, so if there are two roots, then Rolle's theorem says there should be a value of C where the derivative is 0, but that's impossible. Therefore, there cannot exist two roots and there exists So that's why if you set it equal to 0 and try and solve, so if I do the 3x squared plus 1 equals 0 and try and solve, I end up with x squared as negative 1/3, which is not a real number, right? There are no real values that would solve for that. We end up with an imaginary solution there. So that means this can never equal 0. But if we just think of it intuitively, whatever x is, your input, you're squaring that, right? So even if you put in a negative number, you're squaring it, multiplying by 3, and adding 1 to it. So when you square a negative number, you end up with a positive number, which is always going to make, no matter what x is, it's going to make this greater than 0. Okay, so because this is a polynomial, it's differentiable and it's continuous. And then we said, assume that there are two roots, a and b, which means that f of a equals 0 and f of b equals 0. So f of a equals 0, which also equals f of b. So by that, we've satisfied the three hypotheses of Rolle's theorem. Our function is continuous, it's differentiable, and f of a equals f of b. And those just happen to equal 0 in this case, right? Then Rolle's theorem says there must exist a number c such that the derivative is equal to 0, right? So our function satisfies the hypotheses of Rolle's theorem. Therefore, it should satisfy the conclusion of Rolle's theorem. There should be a c in between a and b such that the derivative is 0. But we just showed that that is not possible. So that means that our assumption can't be true, and our assumption was that there are 2 roots. So if our assumption is false, there cannot exist 2 roots. We've also already proven by the intermediate value theorem that there's at least 1 root. Okay. So if we've proven there's at least 1 root, and then now we've showed by contradiction that it's not possible for there to be 2 roots, the only other possibility is that there's exactly 1 root. All right. So don't worry too much about this. They won't put a problem like this on the AP exam. I think it's important to do. It's a good introduction to proof. When you go to college, if you're going to study physics or math, you'll have to take a class. It's usually called, at most universities, it's called Math 300, and it's just all about proof and different types of proofs. And you'll do stuff like this. This is called a proof by contradiction. Okay. Now let's talk about the mean value theorem. So the mean value theorem is just sort of a more generalized version of Rolle's theorem. And all we do to get the mean value theorem is sort of take off the third hypothesis. So the first 2 remain. We still need our function to be continuous. We still need it to be differentiable. The thing we take off is we don't need the y values at the endpoints to be the same anymore. And then our conclusion is that the derivative at the point c, there has to be a number c, such that the derivative at c is equal to f of b minus f of a over b minus a. And let's just interpret this as what it is. This is an instantaneous slope. This is the average slope over the interval a to b. So I'll kind of sketch out what's going on here. It's very similar to Rolle's theorem, except for that last hypothesis we don't need anymore. So we still need our function continuous. We still need it differentiable. So no jumps or gaps, no sharp corners or cusps. But now the only thing we don't need is a and b don't have to have the same y values. So it could be something like this. All right, and then all I need to do is connect the dots with some smooth curve, any smooth curve. Whoops, I had my eraser on. Okay. So what the MVTD tells us is that there has to be a point in between A and B where the slope of the curve matches the slope between the endpoints. There's the slope between the endpoints. There has to be some point where the derivative, where the slope of the curve is parallel to that. And again, it could be more than 1 point, but there's at least 1. So for me, I can see that there's definitely going to be one right here, right? Right about there. There's also probably going to be one over here, where it's going to match up parallel. All right. Below that, this is just an alternate version. Notice all they did was multiplied this b minus a to the other side of the equation. And you end up with this kind of alternate version of the mean value theorem's conclusion. And that can be helpful for certain types of problems. It's not like something I need you to memorize necessarily, because you can always just get there from this one and just multiply b minus a on both sides. Okay. Give me a hand up emoji in the participants window when you're good. I don't want to rush everybody through this. So here's just a couple more examples. And so Rolle's theorem is really just a special case of the mean value theorem. And it's just the case where the endpoints happen to have the same y value, and then the slope that you're talking about, that average slope, will end up being 0. Yeah, Audrey, you don't need the second equation. We can get the second equation out from the first equation. So as long as you have that first one. All right. So let's just do a basic application of the mean value theorem. So it says apply the mean value theorem to this function. By that, what I'm going to do is I'm going to find the value of c. And find f prime of c, where that equals f of b minus f of a over b minus a. All right, well, first, let's make sure we've satisfied the conditions to be able to use the mean value theorem for derivatives. So I'll just make the statement, f is polynomial therefore continuous and differentiable. So by MVTD, the mean value theorem for derivatives, there exists c on the interval from a to b, which in our case is from 0 to 2, such that f prime of c equals f of 2 minus f of 0 over 2 minus 0. All right, if we want to figure out where that happens, where is that value of c on the interval from 0 to 2, here's how you're going to do it. We're just going to continue to evaluate this equation. So f of 2, if I plug in 2 for x, what do I end up with? 8 minus 2, or 6. And if I plug in 0 for x, I get 0. So I'm going to have f prime of c equals 6 minus 0 over 2 minus 0, which is 3. All right, so the average slope is 3. So there has to be a point where the instantaneous slope matches that average slope. So to figure out where that is, let's evaluate the left-hand side of that equation. Let's find f prime of c. So all we're going to do, we're going to take the derivative of our equation and we're going to just replace the x's with c's. So f prime of c is going to be 3c squared minus 1, right? All right, and I'll replace the left-hand side with that. So 3c squared minus 1 equals 3. And now I'll just solve for c. 3c squared equals 4. C squared equals 4 over 3. And c equals plus or minus, don't forget that when you take a square root, the square root of 4 over 3. All right. So the location where the derivative will match the average slope is going to be at root 4/3, negative root 4/3 on the x-axis. So let's kind of, to give you a visual of this. Come on, Bluetooth mouse, where are you? All right, well. Let's just look at this curve on that interval. All right, so I have f of x equals x to the third minus x. How do I add an interval here? No, that's not how. All right, well, we're only interested in the interval from 0 to 2, so we're just focused on from here to here. So I'll mark it off with some points. So we got 0, 0, 2, 2, 6. Okay. So we're only looking at this curve between those 2 points. And so let me connect, let's see, let me connect the endpoints with a line. Y is 3x. All right, so that's the average slope of that curve on that interval. And so what I'm saying is there should be, we found that there are 2 points on that interval where our slope is parallel to that slope. And one of the points should be at that x coordinate, and then I'll just plug in to my function to get the y coordinate. Oh, oops. Okay. Great. So that green point, at that point, if I were to draw a tangent through there, it would be parallel to the blue line. And then there should also be one. Oh, but I just realized I made a mistake. So I wasn't paying close enough attention, but we only care about the interval from 0 to 2, and only one of those points is on that interval from 0 to 2, and that's the positive square root of 4 over 3. So the negative one we can do away with because it's not on that interval. All right, so if I wanted to draw a tangent line just to show you through that point, it would look like y minus the y coordinate equals my slope 3 times x minus the x coordinate. There you go. So there's the tangent at that point, root 4/3, and you can pretty clearly see that it's parallel to the average slope, which is the blue line, right? All right. That's what we just did. All right, so here's another example. Suppose f of 0 equals -3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? And then one other assumption that we have to make. Assume f is differentiable. All right, so since we're talking about a differentiable function, that also means it's continuous. So we should be able to apply the mean value theorem to it. So we can see here, based on their inputs, they're talking about the interval from 0 to 2. And so if I were to apply the mean value theorem, so I'll say by MVTD, there exists C on the interval from 0 to 2, such that f prime of C will equal f of 2 minus f of 0 over 2 minus 0. Now, what we're trying to answer a question about specifically is f of 2. So what I'm going to do is isolate f of 2 in this equation. So to do that, let's just multiply both sides by the denominator. So I'll multiply both sides by the 2 minus 0. I realize that 2 minus 0 is 2. But now we end up with this form of the equation that the alternate form that I was talking about earlier. So f of 2 minus f of 0 equals 2 minus 0 times f prime of C. And then again, I said I'm going to isolate the f of 2, so I'll just add f prime of 0, or sorry, f of 0 to both sides. Okay, so f of 2 is equal to 2 minus 0 is 2 times f prime of C plus f of 0. All right, now we just want to start filling in things that we know, which are, we don't know f of 2. Whoops. We do know that f of 0 equals -3, so I can do minus 3. And we also know some information about f prime of C. Namely, that f prime is less than or equal to 5 for all values of x. So I can replace that f prime of C with 5 because at most f prime can be 5. But then this goes from an equation to an inequality. So once I plug in 5, f of 2 has to be then less than or equal to that. And that's specifically because I replaced f prime with 5. and f prime is always less than or equal to 5. So this goes from an equation to an inequality. And so now I know f of 2 has to be less than or equal to whatever is on the right-hand side of this inequality. And I'll just go ahead and simplify that right-hand side. So 2 times 5 minus 3. F of 2 has to be less than or equal to 7. So f of 2 can be 7 at the largest. Right, pause there. All right. Hold on one second. All right, we're going to do one more example. So this is an example from a previous AP exam administration. Normally I would break you into groups to do this, but today I'll just go over it with you. So hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t, where t is between 0 and 6, is given by a differentiable function c, where t is measured in minutes. And we're given selected values of c measured in ounces in the table. All right. Use the data in the table to approximate C prime at 3.5 and show the computations that lead to your answer and indicate units of measure. So 3.5, halfway between 3 and 4. So the best we can do to approximate this is use the two closest points and find the slope between them. And so that would just be the slope between 3 and 4. So for part A, let's do that. So we're just going to say C prime at 3.5 is approximately equal to and then the y values there would be 12.8 minus 11.2 over 4 minus 3. 12.8 minus 11.2 is going to be 1.6 over 1. All right. Based on the units given in the table, in the chat, can you tell me what the units for my derivative should be? What should the units on this answer be? Good. So derivative is just a slope. Slope is rise over run. So rise is y units over x units, which would be run, so ounces per minute. There we go. Done with part A. And part B, is there a time between 2 and 4 at which C prime of t equals 2? Justify your answer. So this is one where you'd have to go, okay, this sounds like they're getting at mean value theorem. They're giving me an interval. I know that the function is differentiable, therefore continuous. They're giving me an interval on the horizontal axis, and they're asking me about a specific value of the derivative. That's something that the mean value theorem can tell us. So for B, by MVTD, there has to exist some value C on the interval. The interval that they're talking about is 2 to 4. So between 2 and 4, such that f prime of C has to equal the average slope on that interval. So that would be f of 4 minus f of 2 over 4 minus 2. And from my table, that's going to be 12.8 minus f of 2 is 8.8 over 4 minus 2. 12.8 minus 8.8 is just 4. 4 minus 2 is 2. And we're done. Because that's what they asked us to prove. Is there a time on the interval from 2 to 4 at which c prime of t equals 2? Yes, and I actually should be using the names. So let me go back and correct some stuff. It's not f in this case, is it? It's... And they're using the variable t, so instead of c, I'm going to say there exists a t in between 2 and 4 such that c prime at t. And that's it. It's justified. I've named the theorem. Any questions there? All right, hold on one second.